Last thing I want to do with oscillators is talk about the amount of energy stored in the oscillation. From a mechanical system, we have some kinetic energy that's stored in the motion of the mass of the oscillator. It's a half mx dot squared, but we know what x is. We're going to treat this first using a undamped oscillator, and the solution for the simple undamped oscillator is given by this. So we can take the derivative of x and substitute into the kinetic energy expression here, and we get a sine squared function. We can get rid of this factor of omega squared out the front, using omega squared as k on m, and so we have a kinetic energy that is varying as the sine squared. The potential energy is stored in the spring. It's a half k x squared. Substituting in x, we get a potential energy that is varying as the square of the cosine. They have the same factor out the front, which means that when we add them together, we can take out that factor, and then we have a cosine squared plus sine squared. That will give us 1. Finally, meaning that we have a total energy of a half k a squared, which we can rewrite as a half m a squared omega squared. So there's our total energy, and it's a constant, as we would hope, because our system is not losing any energy. We specified that it was undamped. Now I'm going to leave this as an exercise to show that when you do have damping, if we take our solution with damping, provided we are in the regime where the damping is small, so the gamma is much, much less than omega, then to good approximation, the energy will be given by this expression here, or this expression here, equivalently. This expression is actually the same as what we have over here, except now the amplitude here, a squared, is written as a naught e to the negative gamma on 2t all squared, giving us a constant a naught squared and e to the negative gamma t, so that now our energy is decaying at a rate gamma.